The phone in your pocket, the computer lighting up right now, the lasers scanning your groceries, none of it works without quantum mechanics. The entire architecture of modern technology is built on a set of rules governing the subatomic world. But the rules go far beyond microchips. To understand why the sun burns, or how the rods and cones in your eyes process light without being blinded by the infrared heat of your own body, you have to look to quantum physics. It is our most precise, rigorously tested scientific framework. Over the last century, experiments have validated its predictions to an almost absurd degree of accuracy. Yet, despite it being the absolute bedrock of modern physics and our entire technological civilization, nobody actually knows how it works under the hood. As Richard Feynman famously observed, "I think I can safely say that nobody understands quantum mechanics." And he wasn't exaggerating. Today, physicists largely treat the theory like a mindless robot. They feed complex math into the equations, and the robot spits out highly accurate predictions that allow us to build devices. But they deliberately avoid asking what the math is actually describing in the real world. If you try to investigate the foundations of quantum mechanics, to ask what the equations mean, modern physics departments will often treat you with suspicion. It is considered a fringe pursuit, a distraction from serious academic work. The reason comes down to incentives. University hiring committees and grant agencies want concrete, quantifiable results. They want new particles discovered and faster computer chips developed. There is virtually no funding for asking big-picture questions about reality. So the sharpest minds on Earth remain trapped by their own success. They are incredibly good at using quantum mechanics, but to keep hitting those immediate targets, they choose to ignore the underlying nature of reality. To understand why the physics establishment is so hesitant to look closer, we need to look at the comfortable reality that quantum mechanics destroyed. In 1687, Isaac Newton published Principia Mathematica, laying the groundwork for classical physics. This diagram shows a rock being thrown. In classical mechanics, that rock is an object with two definitive properties, a specific position in space and a specific velocity, or rate at which it is moving. According to Newton's rules, if you know those two pieces of information, and you know the external forces acting on the rock, like gravity, you can calculate its exact future trajectory. There is no ambiguity. This idea scales up. If a vast intellect, often called Laplace's demon, could know the exact state of every single object in the universe, it could deduce everything that would ever happen in the future, and everything that had ever happened in the past. For centuries, the universe appeared to be a massive, predictable machine. This mechanical view made sense. It perfectly matched our everyday, intuitive experience of the world. Scientists thought the basic superstructure of physics was solved. Then we invented tools capable of looking at the subatomic realm, and that clockwork illusion shattered. When we look at an elementary particle, like an electron orbiting a nucleus, it simply does not possess a definitive location or velocity. This side-by-side comparison illustrates the shift. On the left, we have the classical idea, an electron orbiting like a tiny planet. But on the right is what quantum mechanics suggests, a wave function. Instead of a solid object with a clean trajectory, the electron exists as a cloud of probability. The darker, denser areas just represent the locations where you have the highest probability of finding the electron if you look for it. And looking for it is exactly what creates the biggest crisis in physics. This is the measurement problem. When left alone, an unobserved quantum system acts like that spread-out wave of probabilities. But the very second we measure or observe it, the system abandons the wave and suddenly snaps into a definite state. Our equations give us no explanation for why this happens. We are forced to confront a reality where the act of observation is fundamental to the behavior of the system. It means what we see is different from what the universe actually is. We have reached the limits of the shut up and calculate era. Ignoring the measurement problem has given us amazing gadgets, but we cannot settle for a framework of reality that remains half complete. To answer the ultimate questions of science, how the universe began, the nature of black holes, and how space-time bends to create gravity, we must understand the quantum foundation beneath them. There are already provocative proposals suggesting that gravity isn't just an external force. Instead, gravity might be a phenomenon deeply linked to the behavior of quantum entanglement itself. We will never find a complete theory that unites the massive scale of gravity with the microscopic rules of the quantum world if researchers remain too timid to examine the actual meaning of their own math. The truth is, quantum mechanics is not a branch of magic. It is not a mystical barrier that is forever beyond human comprehension. It is just physics. To make sense of it, we simply have to free our minds from the classical intuition we use to navigate our daily lives and take the reality of the wave function seriously. If we follow the math without adding a special collapse to fit our intuition, we find that those other probabilities don't just disappear when we look at them. They exist in separate branches of reality. This is the many worlds formulation, the logical result of taking the equations at face value. The nature of our universe is a puzzle that requires us to stop looking at our equations as mere tools and start treating them as a map to what is actually there. We just have to stop being afraid to follow